Hello guys, it's me again. Here we have now a short video on the basics of matrices. I'm again very sorry the video is a bit late. Here we will just cover like the basic arithmetic properties. We will not prove anything. We will just talk a bit about how to arithmetically handle matrices, what constitutes a matrix, how they look like, and what are the important properties when dealing with them in equations and so on. So, quick overview. In this lecture, we will, as I said, just familiarize us with the mathematical properties, and we'll talk a bit about where matrices are applied, what they are useful for. They're an incredible, powerful concept. Pretty young to mathematics, actually. Like they're like some 130 years old, comparatively young. If we compare them, for example, with some other things that we've covered so far, which have been known either since the 17th century or since, the times of Greek mathematicians. So, motivation of matrices. In the last video by Leo, you already saw that when we have a system of linear equations, the general form is always the same, right? We have all of these factors, a1 to akn, and they are like what defines our system of linear equations. Additionally, there's of course the variables x1 to xn and the solutions b1 to bk. However, those are not defining the problem. Those are just giving the framework of the problem. Whether there's a solution or not to a system of linear equations is determined by the variables a. So the motivation to start using a matrix for us is that with a matrix we can shorthandedly express such a system of linear equations. We can just look at the values of a, and this completely covers the system of linear equations. We can use it as a shorthand form. So now we have this shorthand form, which can represent a system of linear equations, but can represent also a lot of other things. We're kind of interested in what kind of mathematical structure this yields. So, first off, for a little intuitive guide, what does a matrix mean? So in a matrix, you have rows and columns, but that does not necessarily mean that a matrix is representing something two-dimensional. I mean, sure, for example, your computer screen can also be expressed as a matrix, right? You have pixels. Pixels can be represented as the variables of a matrix. They each have a value, a color. And your, I don't know, like 1080 by 720 display yields you 1080 times 720 matrix. This is a type of matrix which is not interesting to us, right? This is the kind of computer science matrix which is just used to visually represent things. Because in mathematics, matrices have stronger properties. For really basic intuition, you can think of matrices as a set of vectors. Imagine you have a few vectors, and if you group them together, the kind of space that those vectors represent kind of is what a matrix expresses. We will get deeper into this. There's a very, very close link between vectors, vector spaces, and matrices. But for now, just use it as a little intuitive guide. Every row and every column of a matrix can be thought of as a vector in either n-dimensional or m-dimensional space. Okay, so now let's get to the mathematical properties. As you've seen, a matrix is a mathematical object which consists of, well, frankly, numbers. And for now, let's just assume that everything that happens within a matrix is a field. So if you have a 2 by 2 matrix, every single number in this matrix is part of a field, and the arithmetic of the individual numbers within a matrix shall be a field. So let's say the first variable here on this slide for A. Let's say that this variable is instantiated with 1 over 7 squared times the inverse of root 2. Has to work. We need to have a field in order for everything that we're doing to work. So bear with me. We have this matrix, which consists of multiple entries, and every entry individually is a field, or is an element of a field. So the question is now, taking a matrix as a mathematical object, as an element of the subset of matrices, we can ask, can we add? And the simple answer is yes. If you want to add, you need to have two matrices of the exact same form. They don't have to be quadratic, like they don't have to be 2 by 2 or 3 by 3 or so on. They just have to have the same form. Like a 1 by 4 or a 17 by 3 matrix doesn't matter. It just has to be the same matrix twice. So your domain is basically the set of all matrices of a certain size, and your codomain is exactly the same. So this, as you probably have already noticed, is a group. You have a domain, which is a set of all same-size matrices, and then you have an operation which maps two elements onto a new element, which is also part of the domain. And this group is also abelian, since we have commutativity as a property. As you can see, every single operation we do here is just addition. We add every single entry of each matrix individually, so it's no different from adding within a field, and thus it's just an abelian group. So adding matrices, kind of simple. The real magic with matrices happens with multiplication. And now, before you say what is this complicated stuff, bear with me. This is not something that comes out of mathematics, but this is something that we define that way because it will be useful later. There will be concepts later on which will behave just like that, and here the shorthand notation of a matrix will be very useful in order to handle more complicated problems in the future. Now, something which seems very simple on the surface becomes arbitrarily complicated because we say so, but later on we will have more complicated things, which by use of this operation will become simpler. So just before you start getting angry at me because I'm coming up with complicated stuff for nothing. That being said, if you want to multiply, things are a bit more spicy. We can't multiply every kind of matrix with each other. We can't even necessarily multiply the two matrices of the same size with each other. The necessary property in order to be able to multiply two matrices is we have to have two of them, a first one and a second one, and the number of columns in the first one has to correspond to the I'm sorry. Yeah, the number of columns in the first one has to correspond to the number of rows in the second one. So look at the first one. We have 2 columns and 3 rows. And on the second one, we have 3 columns and 2 rows. So we have an M by N matrix and a N by K matrix. And the rule is that you need to have like an M by N and a N by K matrix. And what happens is basically the n's cancel out. They're like the necessary criterion to have to be able to multiply. And if you do multiply, the n's cancel out, and your result matrix is a M by K matrix. look at the example. We have a 3 by 2 matrix for the first one and a 2 by 3 on the second side. And if you multiply them, then the result, as you can see before I even explain to you how it works, is a 3 by 3 matrix. So the ends, the twos, cancel out. In this case, for example, you could also multiply them the other way around, right? You could multiply the 2 by 3 matrix with the 3 by 2 matrix, and then the result would be a 2 by 2 matrix. So even before we discuss groups, you can directly see commutativity is definitely not given. But now, how do we go about computing the product of two matrices? Well, first of all, you have to know what the dimension of your resulting matrix is. So you look, okay, what's the size of our input matrices? So we have a 3 by 2 and a 2 by 3. So our result will be 3 by 3. So we know, okay, we have a 3 by 3 matrix. And now the question is, how do we compute the values? Well, it works the following way. Each entry in the resulting matrix is defined by, well, I mean, each entry has a row and a column, right, in the resulting matrix. And in order to obtain it, we multiply the values in the corresponding row of the first matrix with the corresponding column of the second matrix. So take the blue example here. We have first row and first column. So we take the first row of the first matrix, which is AB, and the first column of the second matrix, which is G and J. So we multiply A times G, and then we add B plus J. And if we had more values, then we would add all of them up. Okay, and then we go to the second value, which is like first row, second column in the resulting matrix, which is A times H plus B times K. So if you look at it, second column, first row. Okay, so first row is A and B, and second column on the second matrix is H and K. So we get A times H and B times K. And then, I don't know, the very last value is last column times last row times last column, which is E times I. Not to be confused with the Euler number and the imaginary constant. These are just variables. And F times L. If you want, you can, if this is kind of confusing to you, you can look at the example in detail, which number is computed with which, but this is the way we do matrix multiplication. And the resulting matrix obviously is always a quadratic one. So now we can ask a question, what about this operation? So we can multiply two matrices. Does this operation have any kind of property? And the question is kind of difficult to ask. So if you, for example, look at matrices of a certain domain. So for example, you only look at 2 by 3 and 3 by 2 matrices. Then as a result, you get 2 by 2 and 3 by 3 matrices. So this would mean that your result would be outside of your initial domain. And it's a necessary property for a group that if you take two elements as input, the output is also an element of your set. And here, for example, in this example that I just gave you, a 3 by 3 matrix is not part of the set of the 3 by 2 and 2 by 3 matrices. So in this narrow sense, matrix multiplication is not even always a group. If we, as a domain, take all possible matrices, then of course it is a group. However, it is not commutative at all. It is associative, so if you multiply a few in a row, it's fine, but you don't have commutativity. So as I just showed you in the last example, where we have different sized matrices, it's obviously not commutative. But even if you have quadratic matrices, right? If you have two quadratic matrices, then your result is of the same dimension as your input. Even then, commutativity is violated. Here we have an example with two matrices, which get multiplied, and depending on which matrix is first, which one is on the left, we get different results. And this means that we don't have commutativity. So this means that matrix multiplication is a very weak operation, and usually order matters. So usually the meaning of the first matrix is a different one than the meaning of the second one, which we'll see again later on. And now, of course, the question, if this is a group, well, what is the neutral matrix? Well, for the additive group, it was obviously just a zero matrix. Here, it's the identity matrix. I will get to this a bit later in the video. And there's also the question, can we invert this? And this is a difficult question. It has a lot to do with determinants and with linear independence. And just for now, bear in mind that this is a difficult question. It's sometimes possible, sometimes not. And the causality of when it's possible and when it's not possible is pretty important. So bear that in mind for later. It will definitely become a topic. All right. And now the last manipulation of matrices that we will cover in this video is transposition. We're not gonna use it for now. I just wanted to introduce you to it because it is quite important. The reason we do this is that even though we get a completely different matrix by transposing it, many of the properties stay the same. So properties like linear independence or invertibility, determinant, all of these stay the same, even if those things don't tell you anything so far. Doesn't matter. Just remember that this is a very very natural transformation. So what you do is you can imagine it. You draw a diagonal starting from your first entry downwards, and then you use it as a mirror axis, more or less. So basically, here in this example, A and D stay at their place, and they form a mirror axis, and every other value in your matrix is flipped by this mirror axis. I guess it's pretty apparent what is happening. Inversely, you can also explain transposition by saying the index of every single element is flipped. So you have all the indices, right? The first one is 1, 1, then you have 1, 2, 1, 3, and so on, 2, 1, 2, 2, 2, 3, and so on. And you just flip them. So your 1, 1 stays 1, 1, but your 2, 1 becomes 1, 2, and your, I don't know, 3, 5 becomes 5, 3. And of course, if your matrix is not quadratic, then also the form of your matrix changes. All right, thanks for sticking to the end. This is the last slide. Here I just wanted to mention a few important special matrices which are very often used in practical cases. The first one is the identity matrix. So the identity matrix, as I introduced earlier, is the neutral element towards matrix addition. And it's the matrix which has all zeros except on the diagonal where it's all ones. And this one is very, very important. Looks like kind of simple, trivial, but it's incredibly important because it spans all vector spaces. We'll get to it later, what this means. And therefore, it has a special symbol. We just call it En, N in the index. And N just tells us the dimension. But E is talking about the identity matrix. And quite often we will encounter matrices which have the same property that all the values are on diagonal and everything else is zero. And this in general is called a diagonal matrix. Diagonal matrices are extremely well behaved, so to say, because, well, if you think about how multiplication works, we always multiply an entire row with an entire column, right? And the cool thing is that if you multiply diagonal matrices, they remain diagonal matrices because only if you multiply, like, for example, the second row of the second column, the second the two second elements are non-zero. So you multiply the elements on the diagonal, but since everything else is zero, everything else cancels out, right? If you multiply two diagonal matrices, every value which is zero remains zero. So this is kind of the cool thing. And the last special matrix which I wanted to talk about real quick before we get into it deeper later on is the inverse matrix, so a to the power of -1. Mathematically or group theoretically, it serves the same purpose as, for example, the multiplicative inverse, but it works a bit differently. It has, of course, the same property that if you multiply a matrix with its inverse matrix, you get the identity matrix, right? Same thing as with multiplication and addition. And this matrix a to the power of -1 is called the inverse matrix. However, it does not necessarily exist. I don't know, like it exists some of the time. I guess if you have absolutely random values in your matrix, it usually exists, but it's not that its existence is an inconvenience, but later on we will see that we don't really care about how it looks like, but what we often care about is whether it exists or not. So the problem whether a matrix is an inverse or not is oftentimes very useful to solve other problems. So this is a very, very mighty property, whether or not you do have an inverse for a matrix. All right, I hope there's no open questions. Otherwise, again, feel free to reach out or comment. And thanks for listening. Looking forward to see you all again.